Hi, this is Güliz Seray Tuncay, and today I'll be giving the topic preview talk on mobile security. A brief introduction about myself. So I got my PhD in computer science from the University of Illinois at Urbana-Champaign, where I worked on mobile security for my PhD thesis. And since then, I've been working as a security researcher in Android security at Google. So first things first, why do we need mobile security? Because computer security has been a field for many years now, and we have developed sophisticated solutions to security problems. So why is it that we need to take special care when we talk about mobile devices? And how does the mobile shift change the way we think about security? To be able to answer this question, we need to take a look at the differences between classic PCs and smartphones. So first, root privileges are typically not given to users on mobile platforms, and this is because mobile vendors try very hard to keep the platform secure. They don't even trust the user with very critical operations. So second, input is very cumbersome on mobile platforms, mobile devices. So credentials are frequently stored. For example, you don't want to ask the user each time to enter their password. So you'd want to save this password for future use, for flexibility and usability. And complicated security features can drain the battery. So you want to avoid doing that. And network usage can be expensive. Some specific operations like sending an SMS, accessing the 3G or the 4G network will consume data and cost money. And also there's some very unique features in smartphones. For example, in contrast with stationary machines, smartphones come with several sensors. And due to the tight coupling between the devices and their users, the smartphones carry highly personalized and sensitive data. So for example, smartphones have GPS, which provides location information. And since users are mobile, when you have access to location, you can track users. So giving away location information can create privacy concerns, and users might not feel comfortable about this. And also, as I said previously, you can send SMS messages that cost money. You have access, you can make phone calls with smartphones, and these phone calls might contain very sensitive data. You have access to records of previously sent or received SMS messages, which might also contain sensitive data. And besides, you have different authentication mechanisms on smartphones. So for example, you have fingerprint reader. So biometrics are in general extremely sensitive information. If your fingerprint scatter array is stolen, it's gone forever. You cannot change your fingerprint, so you need to take special care when you're handling biometrics. And besides that, you have face unlock. You have trusted places, devices, and trusted voice to be able to unlock your device. And you need to take special care when you're dealing with these authentication mechanisms. Also, how you obtain applications on mobile platforms is different. So we have specific markets for mobile applications, and this provides a new avenue to implement different security features. So in this talk, I will specifically focus on Android and its security internals, but similar concepts exist on the iOS platform as well, but we won't be covering them today. So Android has consistently had the majority of the global market share. Currently, it has more than 80% of the market share. So impact of any security issue on Android is very significant because it will affect billions of people. And in terms of the platform internals, Android has a stripped down and more optimized version of the Linux kernel, and it has embedded web browsers called WebView to display web pages, to allow developers to display web pages in their applications. It provides SQLite databases. It provides software for secure network communication like OpenSSL, Bouncy Castle Crypto API, and the core Java libraries. And it has Java and now also Kotlin language support for app developers. And Android is a Java platform for running applications. Android applications run on Java process virtual machines on Android. And besides, Android also provides a C language infrastructure to app developers. So app developers that want better performance, that they can write their code in C or C++, and this is done with the help of Java native interfaces, JNI. So let's take a look at the software architecture for Android. So at the bottom, you have the Linux kernel, and using a Linux kernel allows Android to take advantage of the key security features of Linux, and allows device manufacturers to develop hardware drivers for a well-known kernel. And this kernel also has some drivers that you won't find in stationary machines. Basically, the drivers to interpret the data that come from devices that are specific mobile devices, such as NFC, gyroscope, accelerometer, and so on. You will find the drivers for these. And on top of the kernel, you have the hardware abstraction layer, which provides standard interfaces that expose device hardware capabilities to the higher level Java API framework. On top of this, you have the native C and C++ libraries, which are used both by applications and system services. So as an app developer, you can use JNI, Java Native Interface, if you want to utilize the native libraries. And here you also have the Android runtime, which is basically what allows you to run Java applications on the Android platform. So you write your application in Java, compile it into bytecode, which is transformed into DEX code by your IDE, which is generally Android Studio nowadays. And this DEX code is more optimized for the mobile platforms and saves storage space. And here you have the ART virtual machine, which is a Java process machine, which is responsible of interpreting and running that bytecode. So on top of this, you have the Java API framework, which is basically a set of object-oriented APIs to make the functionality of the app. So in this framework, you have manager classes. And if you want to use, say, Bluetooth, you will need to acquire an instance of the Bluetooth manager and use its APIs. And on top of that, you have the application layer, which comes with pre-installed system applications, but you can also install third-party applications from app markets. So in Android, applications are self-signed, meaning that the certificates used by Android apps aren't signed by certificate authorities, as in the PKI infrastructures that we're familiar with. And it is an open app market. So Google has its own Google Play Store, which is the official market for Android apps. But besides that, you have the Samsung Galaxy apps, you have Amazon App Store, Huawei App Store, and also F-Droid, where you can get APKs. There's others as well. So side loading on Android is possible, meaning that if you have the executable of the app, the APK file, then you'll be able to manually install this application on your device, which is something you cannot do on iOS. And so as Android is becoming more and more prevalent, so is the malware written for Android. Each year we have tens of millions of new malware being introduced. And there are some very infamous malware that you might have heard of, like the stage fright vulnerability, which is a remote code execution vulnerability in the stage fright multimedia framework library. And in this one, if an adversary sends an MMS message with a video, if the victim opens this message, the attacker can now execute remote code on the device. And this was somewhat of a persistent vulnerability as well. Several different versions of it became available after the initial vulnerability was patched. So besides the security vulnerabilities, we have had in the past various different privacy leaks, and these are generally due to developer error, but regardless, the platform strives to minimize the chances of these happening by introducing several different security mechanisms. Let's now take a look at some of these mechanisms on the Android platform. And so here I would like to start with the infamous principle of least privilege. This is a security principle, which means the practice of limiting access rights for users to the bare minimum permissions they need to perform their work. This principle applies to Android as well. All third-party applications, system services should be operating with nothing more than the privileges that they need for their functionality. And this is done in order to minimize the attacker's impact in case the attacker manages to compromise one of these modules. So to realize the principle of least privilege, Android has isolation mechanisms. And so Android is the multi-user Linux operating system, but here the concept of user is different than that in the traditional Linux-based systems. So here user does not correspond directly to a physical device user, but instead each application is running as a different user. So it has its own sandbox, and traditional Linux-based permissions apply here. The discretionary access control applies here. So you have your read, write, execute permissions for user, group, and public. And in Android 4.3, Google introduced SELinux into Android to further define the boundaries of the Android application sandbox. And this is basically a mandatory access control for Linux, which enforces a system-wide security policy over all processes, objects, and operations using security labels. So using this, you can confine malicious applications. And besides the principle of least privilege, Android also operates based on a multi-party consent model, which means an action should only happen if all involved parties consent to it. And here the parties, the actors, are user, application, and system. And we want the consent given by the user to be meaningful here, which means that if the user is making a decision, this should be an informed decision. Users should understand what they're being asked to do and its consequences. So one of the areas where this multi-party consent model comes into play is Android's permission model. So this model is used to regulate access to the resources on the platform, and to use a permission protected resource, apps need to declare their permission requirements in their manifest files. And there's a reference monitor that checks these permissions. It lies in the framework, Android framework. And for sensitive resources like microphone, camera, and so on, you will get a runtime permission like the one that you just saw, which was introduced in Android 6. And so this was the security mechanisms implemented in the platform, but there's another avenue where we can implement security measures besides the platform, and this is app markets. Here I will mainly talk about Android's official app market, the Google Play Store. So Google Play has some mechanisms in place to detect potentially harmful application behavior. And it has cloud-based protections, and it also has on-device protection. So for the cloud-based one, and Google Play will scan the applications that are submitted to Google Play. It will analyze these applications, and if it decides that this app is displaying potentially harmful behavior, then it will the app will be selected for manual inspection, and if it is decided that this is malware, the app will be removed and the corresponding app developers will be banned. And you also have on-device protections with Google Play. So Google Play Protect app on your device will scan the device for PHA behavior. So it will fetch the executables, the APK files, it will send it to the cloud, which will run the same analysis on these APK files. And then the user will be notified to take action in case Google Play thinks this might be malware, the APK file that it just analyzed. So Google Play has this automated application risk analyzer to decide PHA behavior. And this analyzer takes a multitude of different inputs to identify PHA. So the first one is static analysis. So the app's code here is analyzed. and the features are extracted from it and compared against expected good behavior and also potential bad behavior. We have dynamic analysis here. So Google Play Protect will run applications to identify interactive behavior that can't be seen with static analysis. It also uses Safety Net, which is a privacy preserving sensor network that spans the Android ecosystem and identifies apps and other threats that can harm devices. Google Play Protect also takes into account third-party reports that come from industry and academic security researchers. So these researchers evaluate apps in a variety of ways and send in feedback regarding their findings, and Google Play Protect will take those into account. Finally, Google Play Protect takes into account developer relationships. So it analyzes non-code features to determine possible relationships between applications and to evaluate whether the developer that created the application has been associated with the creation of PHAs. This brings me to the end of my presentation. Thanks very much for listening.